Basically, if you are finding yourself in a special well, um, what you need to do is know a little bit about call it the hidden safety factors. There are hidden safety factors in many of the calculation techniques used today. Um, we will show some of them as we're going through point 5 today with the modern calculation techniques. Examples that I know in the Gulf of Mexico, really deep wells. If you're using the standard calculation software, you'll find that no standard casing will ever be okay. Whereas if you use the modern calculation techniques, where more or less all the hidden safety factors are removed, you see a different picture. All right. I'm sorry to say that we lost let me see, 5 minutes of the introduction here, and the discussion about the separate tutorial video from the recording. I just started the recording, forgot to initiate that. Sorry about that. And I hope again, if you don't want this session to be recorded, that you speak up. All right, well field development, we'll just briefly touch upon that because it's essential to you guys. You'll never know when you're finding yourself in what is called FEED. That's an abbreviation for front-end engineering development. And that's what you do when you're kind of preparing for the very first wells, and you have little data to go by. You may find yourself in that situation. I'm going to give you a couple of tools in this lecture so that you are prepared for a situation like that in your career. All right, so last lecture, a quick recap. We went quite extensively through the triaxial analysis, how we build the picture that we are seeing. The von Mises being the outer frame, and then the horizontal line marked crossing number 2, the black horizontal line there is burst. Number 1 will be the axial tensile, and number 3 the axial compression loads. And number 4 horizontal line below is the collapse area. We should probably have put number 4 here in the compressional quadrant 3. Again, not very often in the literature. Elastic collapse, typically for the larger pipes, doesn't obey yield criteria, so it's a straight line. It's also at the same time the weakest of the collapse resistance modes. So it would be in a way, to make this very pedagogic, it should be up here. And then this line is the middle thing. It should be 2 of them theoretically. One going here, slightly lower for the transition collapse, and then one parallel a little bit lower for the plastic collapse, and the strongest, the yield, should follow the von Mises. Yeah. And number 5 for couplings. In compression, you'll find couplings. They may have some extra restriction on the tension side. Rarely, more often maybe on the compressional side. But these are call it API recommendation. So if you are finding yourself running standard API couplings, this may occur. Yeah. Very often, both pipe and a lot of other products coming out of pipe manufacturing, they are no longer following the standard API recommendation. They are, call it, much stronger and much more improved. That's my observation, at least from what I have seen. Yeah. And very often, for when it comes to couplings, it's often an abbreviation called HC, which means high compression. So, and these are the things that you very often find yourself applying in the industry. We looked at how design and with load cases are with regards to triaxial design, and we talked about understanding the calculations behind and knowing what does it really mean that it comes out of the accepted design area. Should we just give up immediately, or should we maybe consider, is this like a full evacuation? Is that really going to happen? And if it happens, is this covered by cement and not basically very likely to result in a failure? And if you add today the hidden safety factors, maybe that's gonna even tilt a decision in favor of a weaker casing, or if you know that you're going to sidetrack it and there's going to be casing wear, and that's not considered here, it's gonna maybe strengthen your decision in saying, I'm absolutely not using this casing. Yeah, so what you're going to be working on as a professional in the industry will be standards. Standards are important and part of what we lectured the last with the previous lecture. Governing documentation, very often regulations are tied to standards because standards, as said, present a minimum. Today we are going to just touch upon two standards and what is most important for what we have of a topic here, casing design. API specification 5CT or ISO 11960 would be specifications for casing and tubing, and that's their properties, how they are or how they are manufactured. The other standard, we have mentioned it quite a number of times, API 5C3 or ISO TR 10400. That's how to calculate the strength or load limitations of pipes. When it comes to the standard for the specification or minimum manufacturing tolerances, the standards that I'm presenting to you now, they are from 2004, 2005, and I'm not so sure that they have changed a lot, to be honest. Basically because manufacturing, they are doing their thing, and API, they are not necessarily it's better to say it like this maybe. It's like, compare it to car manufacturing. Some are making low budget types for specific areas, whereas others, they are producing high-end luxury things or race cars. So you can't put an API specification as a minimum recommendation to cover absolutely everything, that would be difficult. So to put a minimum is like saying this is the absolute minimum requirements to steering and to braking, and there's a lot of manufacturers of tubulars that set higher requirements than what is put in here to their manufacturing line, and it has improved quite significantly to when many of these standards were set, and you'll see a little bit better what I'm talking about as we are going through this. You see some of the typical things you'll find in the standard here. There's a huge table in there with regards to how to not only have drift diameter, what you can put through, and this is quite important. If you have quite a long BHA that is quite stiff, and you're drifting with a very short item, that item doesn't necessarily catch the call it effective hole diameter, if that makes sense to you. You can, for example, see that from the straightness in the top picture. The effective diameter of a pipe that is kind of crooked would be less than a straight pipe, right? Effective inner diameter. So when you're specifying what you're drifting with, the mandrel you're drifting with, it should not have it should be short, to put it like that. So and it needs to be standardized so everybody can talk about the same thing. Outside that diameter has specifications. We see them here, and the wall thickness in API. We have discussed that quite a lot in relation to Barlow's burst formula. API sets the wall thickness to be the given one, theoretical one, and you have to accept a loss of 12.5%. And pressure testing basically of pipes should be after complete manufacturing. Heat treatment. You guys have seen what heat treatment does, even to the micro subatomic levels. See how that affects the steel and how important it is. So here is a table showing you when it's quench and tempered and when it's just work hardened. So and you'll see what the tempering temperatures that has been applied, and if it's a seamless or if it's a welded pipe. Remember these processes. Yeah. We have also talked a little bit about the composition, and what I remember now saying in one of the lectures where we covered material science is that additives, they are important, and I'm not so sure that I said it. When it comes to chromium, we say that as a bare minimum of 12% chromium, then that's what we call stainless steel. And if you recall, all metals, when it comes to steel, when it goes from a melt to a solid, that's shown through grain growth. And what makes a piece of steel stainless is actually chromium, how that behaves. What happens with chromium is that it kind of puts itself on the grain boundaries. and on the boundaries of the pipe, creating like a film of oxide. It's like I don't have the name for it right on top of my head here now, but it creates a combination of oxide. Like for example, what steel self it does, it corrodes quite fast pure steel, right? Um, on the surface of steel, say that you polish a rather normal piece of steel, it becomes shiny, and you just leave it there. And especially if it's raining or something, or if you put it in the sea like a chain, like a brand new chain, you put it in the sea, it corrodes in a matter of minutes. It turns brown. We know very well what that brown part is. That's the natural state of steel, Fe2O3, for example, or Fe3O4, oxides of steel. And as a matter of fact, that oxide is extremely important for the corrosiveness of steel. Um, if steel kept corroding, a chain that is working as an anchor on a boat, it will be finished. It will be finished and corroded away in a matter of hours. But the oxide layer on top of it prevents more of the components in the sea or air or humidity of the air or the rainwater to further corrode the steel. It's like a protective layer. Rust is a protective layer against corrosion for regular steel. And when it comes to steel with a minimum of 12% mass fraction, it would actually form what we very often see as a shiny surface, whereas aluminum has its natural layer of oxide, which is oblique, not shiny at all. Yeah. So oxide levels, oxide layers, they protect from corrosion, and some oxide layers they are not completely blocking. So what you'll get, and that is part of the corrosion lecture that I'm giving you anyways now. They are not completely blocking. So what you get instead of a complete full corrosion, like an even corrosion all over, is like a local attack, what we call pitting. Yeah. So additives, they are important. They affect the properties and behavior of steel quite significantly. And yeah, I did not share a compendium with you, but I think that in the compendium you'll find how the additives are affecting the steel qualities. And if you don't have the compendium or don't request it, you'll find all the answers to this on the internet quite easily. We will not touch upon more what the additives are doing, but sorry. The different grades, they are listed, the minimum and maximum values of the different properties here, because the additives change the properties of pipes. So there are max min values for the different additives here listed in these standards. We're jumping now over to the technical requirement 10400, or what would be more or less identical in 5C3. 5C3 tends to have, if I remember correctly, a few more details than the 10400. 10400 are is to having all the things that we are showing here, basically because everything here is from that standard, but it would list more of the data behind the conclusions, if you see what I mean. So, and if I, yeah, so that's basically the difference between them. And other than that, they are more or less identical. They are identical. Let's talk about burst and the burst section. Triaxial yield of pipe body. That's burst as it is listed in the standard now. They have completely taken out the standard that you'll find in the software in the industry, the Barlow formula. It's no longer listed even in the front of the standard. It says that in order to calculate burst, you should use the von Mises. It's called the triaxial yield of the pipe body, as said. And of course, as we all know, that pertains to the yield strength of pipe. And there's a specific formula in addition on a separate chapter called ductile rupture of the pipe body. And that's to the end of this tensile strength curve of steel, and that's where the pipe actually ruptures or bursts, as we would say in layman's language. This rupture formula is extremely accurate. And for what reason are we using that formula? Well, in the industry, you're not really using it. It would be in academia, and the theory is to find this point and then calculate backwards where yield actually is. Basically, because it's easier to see, I guess, where the pipe ruptures. It could be other reasons. I haven't really seen any other reasons for it mentioned, to be honest. Clever and Stewart are the guys behind this formula. Clever being the same person who is involved with the modern calculation techniques of collapse. When it comes to burst, the acting forces, we know these are the Lamé principal stresses for tubulars. Inner radius, inner pressure, outer radius, outer pressure, and we always use for R, we use R inner radius. Basically, because theoretically the highest stress level always occur on the inside of the pipe. Yeah. And in order to get the actual stress, we calculate what would be the resulting stress in from temperature stress, from ballooning, from all these factors. Then we get the actual component. Yeah, and sigma, theta, and R goes into and replace these 1, 2, and 3. So 1, 2, and 3, and then you get the result out. But the industry software is based upon Barlow. Down here is a comparison with regards to thick-walled and thin-walled assumption, because what Barlow did when he presented his formula was to say that it's basically valid for thick-walled pipes, which of course it is not, and but it is by coincidence, as it says in the standard, the same as for thin wall pipes, and we know that most pipes, if we have a quick look back to our plot here, we see that the DT ratio of 20 is covering a good portion of our pipes. Between I say, yeah, these are very thick walled, a lot of them. So it starts around here, 15, 16, our standard pipes are not. So basically, you see it quite close here if you're using and assuming that the wall loss is 12.5%. That being said, my understanding is that this is wrong. This is the true graph. This is the true graph. Why? Because the wall tolerance, as it is in most pipes that you will be using from Sumitomo and all the other big ones, they are produced with a complete different wall tolerance. So it is a gap here hidden in the formula, because especially from this factor. Yeah. That being said, yeah, so here it says basically what we're talking about. The stress reaches yield on the ID. The derivation of the formula is incorrect. The background for it, but it has been retained because it happens to represent the thin wall approximation of the biaxial von Mises Lamé failure pressure. So you see it the error goes to zero. It levels out regardless of how you see it. Now, this is an exercise I did once upon a time, and I even asked ISO in Norway to be able to talk about this, and they said yes. So that's why I'm doing that. If you take the data that is available to you inside this standard, you'll see that the absolute minimum of the minimum identified from more than 11,000 different pipes measurements, they give you that the minimum of the minimum is 94% of the wall thickness measured in 2007. Yeah, so that's how it is. You'll find that absolutely most of the pipes would be in and around 99 and to 1% as a normal distribution. And that's for seamless casing here, and that's for welded casing. So that's why I'm presenting very often in this course that the 12.5% is obsolete. The oldest reference, as said, I found to that manufacturing principle and minimum standard in Barlow and in the industry is from 1950, and it's probably much older than that, but it has been kept in API and ISO since before the 1950s. Modern Burst. This is a software developed at NTNU in a master thesis of all things. This is one of the more accurate and modern calculation techniques. It's based upon theory that Lubinsky did in 1975. If you're in one of the one of the places where you can read papers, technical papers from petroleum, you'll find Lubinsky and his paper from 1975 presenting the principles of these formulas. Basically, that's what Lubinsky did he took the von Mises and inserted the principal stresses, and out comes a graph like this. And what it does, when you have zero external pressure, the von Mises is static, and this is basically what you'll find in all industry software also, that the von Mises is static, whereas in reality it moves. It's skewing because of internal external pressure relation and axial stress. Yeah. So moving on to API collapse. A very quick and brief recap follows, because this is basically what it says, and this part is kept in the standard in the front, not in the appendix, like Barlow has been moved. The standards, sorry, the factors F1 through F5 will be listed for the different grades. You remember the formulas and how they are deducted. The borders are deducted through these criteria using the, the factors, and out comes the yielding collapse tolerance. Basically, there is a story behind that you need to know to build more understanding of this API collapse. Since it was developed in the 1960s, and it didn't really take into account any actual stress, and it didn't take into account internal pressure support. So in about 2015, in 2015 actually, that was changed, and this formula was added, the internal pressure. So then it becomes more aligned with the results of collapse testing that was seen. Another thing that was put in at some point was the surface area difference on the inside and on the outside of the pipes. What you need to be aware of is that if you add a lot of axial stress, your yield strength is going to go down quite significantly, because that's what it is. Remember, for plastic and transition, those theoretical, empirical, calculated collapse modes, they are adjusted for yield using this formula now. And what I said when we were lecturing, let me see, where are you? You should be in the beginning. Let me see if, yeah, here we go. So this plot is for yield 75,000. If we go down to say 55,000 psi yield, all of these bars would move up to a lower collapse resistance. If you say P110, all of them would go down. The profile will be kept like this, but everything will just move down. So basically, when you are correcting the yield strength, as you add more tension, suddenly you will have like a big jump on the graph. And this is from SPE paper that was released in and around 2015 for 13 to 8 inch. It has a big jump here, the API formula. You need to be aware of that. And the same thing happens when you add in casing wear. Casing wear will do the same to your collapse rating using this API calculation. It's important to know, and you will feel a little bit insecure. That's natural. When you have a jump like this, what happens just before this jump? Is this real? And is that value on the other side, is that real? So these things I cannot make a firm answer to you, because it would be something that follows the philosophy in governing documentation for your specific company, and it will be your manager that sits with this answer and has to take this decision. All right. I think we stop there, and we will talk about modern calculation techniques after a break. Unless you have any questions, we're just going to jump straight into the lecture again. We share the presentation. There we go. All right. So here it is. High performance modern calculation techniques. There's theory from the previous standard here. Basically, what we're doing is presenting what the standard says as the best formula. As you see here, it's a probabilistic method to as a background for the calculation of collapse resistance. This calculation technique was presented and finalized in the standards released in 2007, and it's been the preferred one in academia since. Most of the industry also use this, and when it comes to special cases. For standard applications in standard software, engineers typically use what we have been talking about all the time. The reason behind this shift to what we call a modern calculation technique was that it was quite a difference between the theoretical collapse resistance and what was experienced in testing. So a rather comprehensive project was started around, was it around 2000? And it culminated several years after. And it's the Clever and Tamano that is the resulting method. It's called Clever and Tamano, and it's a combination of two formulas and work done by these two gentlemen. And it is what we call an ultimate limit strength model. It tells you when it collapses. Yeah. So there is a difference between the approach given in this formula and the API method that says that we guarantee you that it doesn't collapse. until you reach this point. So more or less, yeah. I let that sink in with you guys a little bit. Still, there's safety factors applied on top of that, design factors as we saw on collapse using the API. It it means that basically you don't really have control over your safety factors where they are. Basically, it has been forgotten. You cannot find in any literature what the safety factor is for API collapse formulas, and it won't maybe make sense either because it's put across absolutely all manufacturing processes, across plants, across anything related to yeah. So again, the analogy to cars, you have the cheap economic version and you have the luxury version made for endurance and speed and whatnot, and you have the same standard, right? And the same safety factor. So it's a little bit special. Whereas when it comes to the modern calculation technique by Clever and Tamano, you put in the specific properties that the pipe has, and you know when it collapses. That's a theoretical difference between those two methods. What is the background of Clever and Tamano? Yeah, you'll see the yield strength, ovality of the pipe, eccentricity, residual stress, outer diameter, wall thickness, and collapse pressure. If you have the specific distribution measured, and trust me, they do. The manufacturers, they have all this data, and they know the result of this. But still, they would like to list their data differently, and these details would not be publicly published as per se. Yeah. And once you put these data through the calculation, you'll get a distribution like this, a normalized performance distribution, and you can set your own standard deviation. Now, the proposal, what we did when we developed a software for collapse, this modern collapse performance at NTNU, and of course, what we did was to add the element of wear. So you now, based upon this method, we modified it so that it also includes wear, and the result you'll see later on is the most accurate collapse prediction for realistic pipes in the industry, at least at the point when it was presented a few years back. What we do is make our own decision with regards to standard deviation in this case, saying that okay, it is probable that 2.5% of the pipes, they will collapse given the strength of say 9,600 psi here. Only this portion would collapse. You can do it different also. You can use 2 different standard deviations or 3, whatever you feel like, and then you apply your design factors, which takes away what, 10% of it. So you end up with taking away 1,000 psi, meaning 9,006 going down to 8,006, meaning you're here somewhere. Yeah. So that's basically how you can control your safety factors. You can also go whatever you feel like on the standard deviation. So here you have the numbers, the exact numbers for your pipe and the strength how it will perform. Now this this normal distribution you see here is theoretically unrealistic. Why is this unrealistic? These are numbers based upon what API work group back in the day did for Clever and Tamano. I'm calling it unrealistic. Why? Because today, when you're manufacturing and buying manufactured pipe with, for example, Sumitomo or with others of Valorec, with all the big ones, they will give you the specifics, and the pipe batch you're having will never have the distribution given here. This distribution is basically based upon a worldwide manufacturing, and it's a distribution behind the yield strength. It's a distribution by the ovality that is much wider than what you'll get for your pipe batch. You can put in your much more narrowed down, accurately measured parameters for each of these parameters. Ovality, for example, it will be much more narrow than for the worldwide production, given that the standard deviation and the normal distribution, sorry, would look much more narrow than this. Yeah. So that's the strength of the new modern calculation techniques. It takes away a lot of the, call it, unrealistic safety factors or even the hidden ones. So many feel confident using these methods. I know for a fact that big companies in the Gulf of Mexico, as said, they use this in extreme in extreme wells. Yeah, and basically more than 4,000 pipes were collapsed in the work from 2000, and 11 different calculation formulas were compared, and it was a broad consensus in the work group that the new collapse strength formulas are more accurate than the old ones. The old ones meaning the ones that API presented based upon the empirical values of the performance of pipe in 1960, the ones that the industry are using in their software now. Yeah, so you can read more about this. Basically, what what prevents the industry from moving over is the fact that not all worldwide production is covered by the probabilistic data, someone says, and I'll add something to it. I think from my perspective, and wearing my type of filter glasses. Basically, again, what works, you don't change it, and there is a quite varying degree of understanding of casing wear in the industry, and letting a lot of engineers loose with an ultimate limit strength type approach, that would be maybe not so wise. All right, that might be one of the reasons. Yeah, here's a full overview of the appendix. Discussions of the triaxial yield of the pipe body. That's more, call it, flesh on the bones for the formula presented in the previous part before the break. Discussion of the historical collapse formula, the API, and then the probabilistic collapse. That's what we talked about now. Yeah, a lot on the collapse formulas are discussed here because it's quite a big step. It's quite a big step from what we had, what we are using in the industry software. There are a lot of other topics that you need to know when you're working with pipes in your career, working with casing design. What we need to know, I'd say that yield limit inner surface, that is what we call a hidden safety factor. It is absolutely true that the highest stress occurs on the inner surface of the pipe. However, when you when you look at yield, is 0.2% deformation, and will that occur on the inside of the surface of the pipe only? I had serious doubts that this actually is realistic. Um, and what will happen if you reach 0.2% yield on the inside of the surface, and then you relax it? Absolutely nothing will happen. That's what I understood at some point, and I discussed this with other professors in other departments, and typically, just so so the perspective is clear, Mr. Lamé, he gave us the principal stresses for pipes, whereas a professor constructing or a professionals constructing a bridge, they would have to find their own principal stresses and or use the torsional parts and go from scratch on every single design, whereas for us, most of the job is already done. And in that context, casing design is actually simple because you're working with the same um, object all the time. It's a pipe. Whereas those who work with a different understanding, basically going from scratch all the time, they say 0.2% deformation on the inner side of the surface doesn't really do anything for the pipe as per se. Nothing. So what has been discussed, and you'll find a few papers on it in the literature, what we call through wall yield. You need to go with 0.2 yield stress all the way through the wall of the pipe in order to get any sort of deformation. And with that being said, I guess this collapse, this collapse is not touched by it. It's the burst. The burst formulas are actually touched upon it, unless you're talking about yield collapse. Okay, so that's clear. So the Barlow formula is again call it yeah, the one that is being debated as is it really accurate enough? Yeah. Buoyancy. This is the formula for buoyancy for multi sized strings. It is not very complex in itself. You just add all the different sizes and the buoyancy factor will come out. It's basically the single step that was shown before, but when you come to a crossover string, you need to do this stepwise exercise, following the parameters here. I think I mentioned it before, but what you need to know is that the yield of steel is affected by temperature. Yield of steel is affected by temperature. percentage of yield typically is reduced from room temperature to 100 degrees, around 5%. Very often, when you're dealing with components, not pipe, but components, you need to be very aware of what would be the yield given at. Is it at room temperature, or is it at 100 degrees, or what is your reference temperature? And you need to know um, the specific material you're working on, its composition, because it varies with different compositions too. Some they go to 3 and some they go to 7% yield at 100 degrees. And as you see, it falls off with more temperature, 150, even more degraded. In the industry, out in the fields, typically where you find land-based industry a lot, you see papers or people talking about the quick and dirty method of looking at the triaxial stresses and finding what is remaining. I do not recommend this for any other purpose than what you do when you go into the grocery store and you want to know what to expect to pay. That you do like a rounded off accumulation or, per item you're purchasing to see that, okay, in the range of $100 what you're going to pay, for example, right? So here is what you can do for this too, to know that, yeah, I'm within the limits. Basically, this method is based upon understanding the yield. So if you're having some sort of actual stress and your yield is well, the actual stress is 10% of the yield. It means that you reduce your burst rating with the same percentage. Yeah. And then you're using the graph like this and say that it's 90%, 6% of yeah. That's how the procedure is. Find on the graph your 10% actual stress, see the cross section with von Mises, and then read off an approximation of what the burst is, and the same with collapse rating. Now again, this would only be valid for yield strength collapse, of course. If you're moving to other types of collapse, I could not really say if it's valid or not, to be honest. Yeah. So be very careful with this. You'll find this in the industry, and now you have a basic introduction to what it means and what it does, and to be careful with it. What is interesting about casing, worn pipes? All pipes are worn, more or less. As soon as you start drilling, remember the picture of the pipe hanging suspended from the top drive. It has tension from the neutral point that would typically be very deep in the well, and it will be on the inner side of the well. Pipe, no matter how you run it, it will always be to one side of the well, meaning there will be some sort of contact. And when the places where you would not have much contact would typically be close to the neutral point, and then in the compression again, with a significant portion of compression, you would find that there's a contact on the outer curve of, of the well bore, yeah, or casing for that matter. So we need to consider, with that in mind, the burst. The burst affected the burst strength, the burst limitation, burst loadings that the pipe can take when it's worn. You use just any of the formulas, and you adjust for the remaining wall thickness. You see a wall thickness mark, T mark. It is the remaining wall thickness as in this picture. Now, when it comes to collapse, the story is quite different. It's not straightforward at all, really. You have an approximation and rule of thumb in the industry. You won't find, as I said, any of this in any standard, or there's no software basically that provides a rating as per se. You see an encasing wear that they allow some wear, and basically that's built on this formula, again Barlow, with its accuracy, and then API formulas. What they do is 1% wear equals 1% reduction in collapse rating, and it's valid up to as much as 30% from there on. No, not applicable for use. So with that being said, is the result accurate? Remember what I said about API collapse rating. If the yield is changed because of actual stress, the calculation of reducing the yield in order to get that, yeah, you know, and this wall thickness is the same. The DT ratio will change. So that means that you will have at a certain point you will get another collapse mode just from the change in wall thickness. Yeah. So that being said, this is what the industry uses in its software. Of course, at NTNU we were not happy about it, and we had to do something about it. Here is the drawing again of the effect that you change mode. Yeah. So we had to do some approximations. What do we do? And we ended up using Clever and Tamano, and we used a method, some very specific mathematical methods. Now, what is interesting, I think, is that elastic collapse is a fully mathematical developed. It's not correct to say collapse, like I said before. It's an instability calculation, buckling, and whereas in yield strength collapse, which also is a mathematically derived calculation, both of them very accurate if you use this API or not. The only thing coming into play with API yield collapse would be the through wall yield criteria. Now, when it comes to Cleveland Tamano. It's again fully mathematical derived, also for the midsection with the instabilities. And with the stress concentration factors, we also use mathematical methods to come straightforward. And you see the oldest and I don't know many methods of calculating collapse for worn pipes. The one that we found that had some reference in the industry and application and was kind of accurate was the Kuriyama model. And our model that we developed is actually improved compared to Kuriyama. If my mind is serving me well, Kuriyama he based his calculation method on Tamano's formula that were older than the combined Clever and Tamano improved model. So that might be the difference. It's 36 actual collapsed pipes that were mathematically calculated compared to their real collapse values, and as you see, the accuracy is quite quite impressive. Yeah, you'll find all of this in the SB paper up here on top. Yeah. Now, there are a few other things that you guys need to know as new um, uh, drilling engineers and professionals. Pressure testing. There are some aspects like inflow testing with a plug. You have heard about it, I guess, and acceptance criteria. Typically, the duration will be discussed. How much loss or increase will be accepted. Now, in most governing documentation, you'll find that 0 is the number. That is, of course, not what we normally see. What we normally see is an adaptation of the system. A piece of steel is ductile. Formations in the ground are ductile. Your fluid compresses, and it also does expansion. One thing will be under pressure, that will be like an immediate effect, but then comes the temperature differences in the well. It's heated up, and you'll see changes in pressure from this also. So this is what you need to consider, and this is covered in a way in your governing documentation that you need to understand. It should level off. You would typically find it should level off. You should see a clear leveling off, and there will be like a tolerance in that leveling off. And typically also let's have a look at this graph. This graph is something that is quite useful actually. The red line is actually an accepted graph, and the blue is not. It drops off, and it takes longer and longer, but it still drops off too much in the time frame that you're looking at. It depends. Flattening trend, these are the typical ways you would look at it. You may find an area where it's within the 5% deviationing, and it is flattening out because it's longer between the loss. But it would be typically difficult difficulties always like this in pressure testing. This graph having a constant pressure to the second decimal in the same time frame. Yeah. Quickly touching upon field development. what we do is front-end engineering design. We start with material quality. That's typically something that is assigned to a special material science group. We will have to acquire pressures and the composition of the fluids to be produced, so that and rates, so that we understand approximately the phases that will be existing in the well construction. Will it be gas? Will it be liquid only, or so on, and any scaling potential, so on and so forth. We need to understand. We need to understand this and give it to the material science group that then simulates if you need special pipes, or if standard pipes are good enough. Then and that is talking about material quality and corrosion only. Basis for design is what you are developing. You're developing a casing design and a tubing design, and then you're developing a drilling design and a completion design. All of these things are tied together. If one changes a little bit, you are very often affecting the others. If you change trajectory, typically that affects the casing design, and the drilling design, meaning torque and drag, so on and so forth. If you try to save something in one end, it usually affects the other in not a typically positive way. Yeah. And you do this design for more or less all wells. You find your outer layers. If there's a vertical well, if there are extreme ERDs, you do the designs and you see what would be in the middle. You need to kind of have a frame. This is what I'm going to do. And then you make your orders of casing and long lead items. Typically, once you have scoped the number of wells and you know that part, that's typically front-end engineering design too, the number of wells and their designs, then you need to contract suppliers of Christmas trees, tubulars, or casing tubing liner called OCTG, Oil Country Tubular Goods. You need to contract all of them and have these things delivered, and you need to do that very often minimum 1 year in advance, because that's the lead time of these items. Yeah, so having like an overview of what you're going to need and purchase, that's what you need in order to do the contracts, and the contracts needs to be in place at least 1 year in advance because of the lead time. So there you have planning backwards: 1 year delivery, a half a year for the development of the contracts, and I don't know how much time in order to get all these designs in place. Then you have the time aspect of it. Yeah. Yeah, there are different things. We have talked about annular pressure buildup and this special pocket before in our lecture, so I'm not gonna go into that again. What you will do in a situation where you find yourself in an area where your company does not have data that are relevant. Say you have a very limited access to data. I found myself in that situation once. There was a field where exploration wells were done so far back that basically the data was not um, available. Uh, in some summed up, not available. So what we did was to go to what was called Rushmore before. It's called IHS now. Um, and you can click on this link to find a brochure from them. At least that's what you could before. You can just search, I guess, for IHS Rushmore in on the internet, and you'll find what they do. They collect data worldwide for all operators. All operators report this um, to to them, and you pay a service fee, and then you get data out. Um, I guess I guess there's a company in Oslo also doing similar things. See if I can remember their name. Stad at something at the end. I can't remember. They are they are actually quite good, and they can they work with predictions as much as the price of steel and a lot of other things. I'll see if I can if something jogs my memory. um, they are located in Oslo, and they are very good too. But I'm not so sure that they are detailed in the drilling performance as the same degree as Rushmore. Um, Let me see. Local governments data. You'll find that in many countries. Um, uh, in Norway, you can go to well, this is what you find with Rushmore. This this is what you find. This is what you this is what you find with Rushmore, and there are others you can find with the local authorities. In Norway, it's quite comprehensive what you can find. It's quite comprehensive what you can find. Um, very very good resources when you find yourself in a situation where you're developing a field and you absolutely have no data. All kinds of data. Yeah, casing design from scratch. You do that, of course, from the bottom up. Given that the subsurface team, they are talking about specific hole size through the reservoir, and of course, given the fact that they say you have to install a minimum tubing size for the production rates, so that you start from the bottom. Basically, that's how casing design works. And where there are significant risks of needing to add a section, you of course need a contingency hole size. That could be a drilling liner or so. Yes, I am working home office today with some helpers, and you've been hearing them, I guess, in the background. Now the time is up, and so is this presentation. So please raise your hand if you have any questions or comments.
Um, I just want to ask regarding the two lectures that are not being covered, the plug and abandonment, and the other one on corrosion. I think you said you have recorded versions of these two topics.
Yes, that's true. From last year, I believe they are covered, but not. I would like to do them different and more to the point at some point. If you want me to, I'll see if I can make something. I will have to see if there's what I can do. To be honest. Yeah, and they would be extra for you if you see what I mean. They will be extra. They are not in the essence of casing design context. Yeah. But I'd like to touch upon a topic from my point of view. I feel I have a few things that could benefit you in the in your preparation for your career.
Okay.
So if you want me to, I'll see if I can if I can if I can help you with some input there if you're interested. Any other questions, comments? All right, with that, I'm going to say thank you guys for listening, and I would wish you all the best in your careers and in your preparation for your careers. Thanks.